So let's welcome last speaker for today's session, which is Pérez Millán. He comes from Fyla and also a startup from Universitat de València. Welcome.
Okay, thank you very much. Thank you very much, Pascual, for your introduction. Well, first of all, I would like to thank the organizing committee for inviting me to this to give a talk in this frame. When Ruben phoned me to invite me to give a talk in Photonic Integration Week, my first reaction was that I was not the appropriate person to give a talk in photonic integration, because we at Fyla we build fiber lasers, and we use optical fibers and optical fiber devices to build these lasers. So, but he reminded me that we had some applications in our website where we claimed that our supercontinuum sources were useful for applications where photonic integration has a lot to say. So he was right. Indeed, our supercontinuum lasers are an optimum source to characterize photonic integrated devices and circuits. And on the other hand, in the near future, supercontinuum technology will need to offer more compact devices, more compact versions to the market, since many sectors are blocking the entrance of supercontinuum technology because of its size, its weight, and its complexity. So probably photonic integration has an important role for this to be a reality, for manufacturers to be able to offer the market more compact supercontinuum sources. So this is why the title of this presentation, which is Perspectives of Photonic Integration in Supercontinuum Technology. The structure of the talk will then be as follows. I will briefly introduce Fyla, who we are, what we do, what we sell, where we do sell, and what a couple of applications, of interesting applications that I want to stress out, which are those where we are entering with more success the market. Then I will move to explain why supercontinuum sources are optimum to characterize amplitude and phase properties of integrated photonic devices. Then I will summarize my vision, my opinion about how photonic integrated devices can help manufacturers as Fyla to integrate, to make a more compact supercontinuum sources. And finally, I will conclude. So, Fyla is a company based in Valencia. We build fiber lasers. We have different types of lasers, but all based in fiber. And they emit in the ranges from continuous wave, nanosecond, picosecond, and femtosecond pulse widths. We are one of the very few companies in the world that are controlling the supply and manufacture of those devices that are composing our lasers. That's a big advantage. That's really one of our most competitive advantages, the fact that we manufacture our own key optical fibers. So we are, well, the central site is in Valencia, the R&D department also, and our factory is in Barcelona. We are currently selling our products all over the world. In the main countries in Europe, we have customers. We also have customers in Asia, Japan, China, Korea, and also in Latin America, in the main countries of Latin America, Brazil, Colombia, Mexico, and are now working into entering the United States market. So that's a brief summary of what we are and where we are. So one of our products is the Supercontinuum laser. Supercontinuum laser is a white laser. The principle of how we generate a white light laser is, in principle, simple. It is just that we use a photonic crystal fiber with the proper dispersion and nonlinear properties to convert the wavelength of a conventional laser, which is monochromatic, into a white light laser. This is done thanks to those highly nonlinear properties of the photonic crystal fibers and the dispersion management of the manufacturing of these fibers. So we combine with a laser the properties of a lamp, which is this very high broadband emission, with the properties of a laser. We have a spatially coherent source with very high brightness and directionality. So what we have is a laser beam of white light. These combined properties offer unparalleled white light brightness. That means that the sensitivity of the measurements that we can do remotely of different samples is very high compared to other sources. It is very easy to integrate because optics are easy, and the access to that light is easy because directionality is kept throughout the whole optical path. And well, one important property of these lasers is that they require low power to emit very high brightness compared to their competitive technologies. So this, here you can see the different references that we have currently at Fyla. These are two different types of supercontinuum lasers, the reference SC and the reference SCT. The SC reference is a laser which is a chaotic laser. It is emitting pulses chaotically with a repetition rate in the range from 30 to 50 kilohertz frequency, with pulses of several tenths of nanoseconds. This is a very useful source, white light source, whenever you want to use high energy pulses. Applications requiring high energy pulses are applications where this laser is very useful. In the case that you need a very stable source and with a very high repetition rate, then what we offer is the SCT. It is a source that emits pulses at a frequency repetition rate which is fixed, and it is of 20 megahertz. Since it is based in mod-locked lasers, it is very stable, both in amplitude and phase. And it is useful for applications where you want to use it just as if it was a continuous wave white source, or applications where you need synchronization. Synchronization like lifetime fluorescence microscope measurements, for instance, where you need to synchronize your pump and your probe and see the lifetime fluorescence of a material, for instance. So whenever synchronization is required for your measure, then this is a very good solution for your system. Both are compatible with a tool that we also manufacture and sell, which is an accessory to tune the emission of that laser working as a filter. It allows the user to use each of our references, changing the central wavelength from, in this case, which is the reference for the visible range. You can move your central wavelength from 450 nanometers up to 850. And what is more important is that you can also change the line width or bandwidth of your emission, typically from 5 nanometers up to 300 nanometers. So I will stress out a couple of applications where microscopy, where the market is is understanding this technology and is buying our technology. One of them is confocal fluorescence microscopy. In these lasers, in these systems, advanced laser microscopy for super resolution imaging, confocal microscopy is used to take images from samples which are dyed with fluorescent components, with fluorescent fluorophores. Okay, so to take an image, you need to excite with a given wavelength where that fluorescent, where that fluorophore is sensitive. So to get a composition of an image with different fluorophores, you need a set of many lasers, many laser lines, each at a given wavelength. So this is the standard way to work with advanced laser confocal microscopy. It is clear that our supercontinuum source might be useful to eliminate the need of several laser lines with just using one single supercontinuum source and with using the arbitrary spectral filter that I told you before. This is something that one of our customers at ICFO has demonstrated with taking images with even with the same or even higher resolution than with standard laser boxes. These are some pictures of their setup. You can see here the conventional box of lasers that are feeding a standard confocal Nikon SC1. This is a setup that you can see how complex it is. You need different technologies indeed of lasers to have different lines from blue to red in their case. And it is all free space that has to be coupled to a single fiber. So the replacing of this set by a supercontinuum laser simplifies enormously the way of illuminating or feeding the microscope with white light. So just with a way of just with the system of selecting the bandwidth of and central wavelength of the emission, you can just, for instance, illuminate with green light or illuminate with red light that sample. That sample, in the case of red, will be dyed with a fluorophore sensitive to red, and in this case sensitive to green, just with a single source. And this is one of the examples of how is this setup performing. It is an example of cells of the type BSC1. The nucleus of those cells are being dyed by a fluorophore which is sensitive to 568 nanometers, and the microtubules of the cells are being sited by are being dyed by a fluorophore sensitive to 647 nanometers. These are images of different planes of the sample, and in this technique, what the researchers do is to differentiate different components of the cell and then make a combined image. The result is a very high resolution image below 1 micrometers with very well differentiated components of the cell. What is very interesting and of which we are very satisfied is the fact that the parameters, the standard parameters of the confocal microscopy are the same that are being used, or even better in the case of using a supercontinuum source with regard to a set of laser lines. We are taking images at a 1 second frame rate and with gain of the photodetectors in the low range of a value of 30 compared to a maximum of 256. So it is completely comparable to the more standard technical way and technical approach, and even better in some of the applications. Moreover, this laser has been used to make in vivo imaging. Here, what you are seeing is a sequence of images of a type of cell that has a axonal growth behavior. It is a type of cell that is used by researchers to simulate tumoral neurons, how those tumors are being grown. What is very satisfactory of these images is that this image has been taken, it is just a sequence of images of a measurement of 30 minutes, and the image is of very high quality with very high resolution and without different values of the power obtained. So that is possible thanks to the stability of that laser source. Another application is food sorting. I won't go deep on this application, but the idea is that you can use a supercontinuum laser to take the spectrum remotely of a given food sample. If that spectrum is correct, if that spectrum, then the sample passes the quality test. If it is not correct, if the spectrum indicates that sample is not healthy, then the machine eliminates that sample. So it is a food sorting machine. These machines of one of our customers has been able to work at a sorting rate of 6 tons per hour using one supercontinuum laser. Okay, so once I have just gave you a couple of insights of our applications, I will explain why supercontinuum sources are optimal for photonic integrated devices characterization in the optical domain. Well, what are the advantages? Well, so since the light is generated already in the single mode core of a fiber, you get typically spectral power densities over 40 dBs compared to other light sources that has to be coupled to the light that to the fiber that is being used to characterize the device. You have a single source for the whole visible and infrared range, so you do not have to change your source depending on the band of the device that you want to characterize. And what is very important, and this is something that I have seen having a look to publications on this application, is that typically the integrated devices are very small. So to really understand the band gap related phenomena of those devices, you need a source of at least or close to an octave spanning of the central frequency of that device. So if you want to really characterize your device and identify and characterize the transmission resonances, you need a broadband device with wideband with bands over octave spanning. This is by far offered by a supercontinuum source, and finally, coupling to peaks is possible with low loss compared to other sources. Okay, these properties have been used since 2005, 2004, where seminal publications demonstrate or suggest the use of supercontinuum sources to characterize photonic crystals. In this case, Rakic and collaborators do their own homemade supercontinuum laser with a spectrum band of roughly 800 nanometers to characterize the resonance of a 1D photonic crystal microcavity. With that source, they are able to detect and characterize completely the whole stop band of that device and measure the transmittance of the resonance between the forbidden band. Even before, even earlier, Q and collaborators suggest the use of a supercontinuum source to characterize a 3D photonic crystal photonic crystal with dielectric point defects as this one that you can see here. And again, they are able to take not only transmission but also reflection spectra of their device, launching the supercontinuum light to the sample by using lensed fibers, which is one of the techniques that is standardly used currently in labs. In this case, the source in this year is about 800 nanometers broad, and they are able to focus that spot into a 2.5 micrometer diameter with calibration reference, which is the adjacent silicon to that photonic crystal. Well, nowadays the supercontinuum laser is broadly adapted by many labs in the world using commercial supercontinuum sources. The technology has gone to offer supercontinuum lasers with acceptable prices, with very broad emission bands from the far visible to the far mid-infrared, to the close mid-infrared. They have very good temporal properties for those applications where synchronization and time response is important to be measured. And what is indeed more important for these applications is the stability. This is one of our references that is offering very well average power, which is below 0.5% full spectrum average power, standard deviation, and also peak-to-peak, in case that temporal performance is important, is with a stability below 0.6% in the infrared and 1.0% in the visible. Visible is always less stable because the fission of solitons which generate the supercontinuum in the visible make that process is less stable than the first process that generates the infrared emission. And well, in particular, several of our customers have been using our sources. Fraunhofer, the sensor group of HHI, acquired one of our lasers to characterize hybrid integrated microring resonators for CO2 detection in amplitude, to check the resonances, how they change when a small portion of graphene is placed in that ring. And one thing that worried this group was how to couple properly the light into a very small photonic integrated device. And we offer the solution of tapering down the photonic crystal fiber, which is at the output of the supercontinuum source, so that it acts as an inverted mode field adapter, so you don't lose light because it is guided by the nucleus of that fiber up to the size of the photonic crystal device. Since this is a guide which is surrounded by air, the light is not being out of the nucleus, and all the light of the supercontinuum goes to the device. That is even dangerous because the power is very high. So, but the coupling is very efficient. Up to now, the pictures that I have shown are related to amplitude measurements of the optical field of the device under test. But supercontinuum sources, stable supercontinuum sources, are very useful also to measure phase properties of these devices. This is an example of a work done by the University of Valencia with our supercontinuum SCT. And it is a very simple setup based in fibers to measure the dispersion curve of a fiber, of a crystal, of a photonic crystal fiber. This is a photonic crystal fiber, but it can be any photonic crystal or any device which has dispersion properties. The idea is that if you place the sample in one of the arms, and you change the distance of the other arm, then you have interference fringes that indicate what is the dispersion in that device. Typically, this is interferometer system, which is standard, that to obtain the whole dispersion curve in the whole spectrum that you want, you need to change the superluminescent LED at different bands. So it is tedious, it is not robust, and it takes a long time to have that dispersion curve because you have to change the different diodes. So the idea is to replace that LED by a supercontinuum source. In this case, an SCT500 from Fyla was used. This is the setup. And this, as I told you before, is a source which indeed has the possibility to synchronize your output with your measurement. Here, I don't know if I can. Okay, there was a video here, but I think I cannot play it. Anyway, the idea is that here you can see two pulses, each of them with the whole spectrum. They're white pulses. One is coming from one arm and the other from the other. When they are overlapped, then you have a very high interference fringes with very high visibility, and then you can get all the spectrum, I mean the whole dispersion curve with a single supercontinuum source, just synchronizing those interferences with very high visibility of fringes. So only one source compared to this makes that this system is nearly an automated technique to have a whole dispersion curve, which is not easy, and there not exist really commercial systems to deliver these measurements. So that's possible thanks to these supercontinuum sources. Okay, so finally, I will try to summarize what is my opinion about what I told you before, that photonic integrated circuits can, how they can help supercontinuum technology to move towards a more compact references that help manufacturers to unblock some markets that require those compact systems. As I told you, there are several markets that unblock the entrance of these sources because of its size, its weight, and its complexity. Its complexity is not the problem. The problem is the cost derived from that complexity. Some of them, and which are markets that are growing steadily and very fast, are those related to personal handheld devices in healthcare and food. Another, which is pretty obvious, is what if we install a supercontinuum source in a drone to aerial inspection? That has a huge potential, but the weight is not yet low enough to be installed in a drone. And definitely manufacturing industry, our customers in those sectors understand very well the potential, but the cost is still too high. So we need ideas to offer our customers more compact, light